In this video, I will give a brief reminder of what Gauss's law is and a few of its applications. So we will begin by remembering what the electric flux is, and then we will go to the formulation of Gauss's law and see several examples. The electric flux is a mathematical quantity that corresponds to the actual number of electric field lines that penetrate a given surface. We normally denote it with this symbol, this Greek symbol here, and its units in the international system are Newton per coulomb times square meter. To put things simple, we will imagine in a first attempt a uniform electric field that is given by these lines here, and plane surface given by this green plane surface here, denoted by A. A is the area of this surface. So to calculate the electric flux across this surface, as we've placed the electric field perpendicular to the surface, the total electric flux is as simple as multiplying the electric field times the total area. Okay, so this is for a very simple example. Now we will think of complicating things a bit further. I will think that the surface is not parallel. Now the surface, we call it here A2, is not completely parallel. There is an angle between the perpendicular to the surface denoted by N and the electric field, and this angle is given by theta. If you realize the number of electric field lines that are crossing A2 is the same as the ones that are crossing A1, which is a surface perpendicular to the electric field, and which is related with A2 with the cosine of theta. So you can say that the total flux across the surface A2 is going to be the same as the electric field times the surface area of A1, okay, which is the electric field times A2 cosine theta. And this can be put better in a better notation, saying that this is equal to the scalar vector multiplication of the electric field times the area times the unit vector in the perpendicular direction and the direction perpendicular to the surface, which can be just signaled as E times scalar vector scalar multiplication A, where this A is equal to the total area. It's a vector that has the total area as a modulus, and the direction is just the perpendicular to that surface. In a more general example, we can think of a surface that is not plane, that is completely, that might have any distribution. And this is an example here. And for any surface like this one, what we can do is divide it in very small plane surfaces. Each of these plane surfaces is going to have an area differential of A and a direction normal to that plane. So we providing this as the element of area, okay, this differential of A as a vector that is just perpendicular to each little segment of little segment of surface, we can say that the total electric flux across that little element of surface is going to be given by differential of the electric flux, and is equal to the vector scalar multiplication of the electric field times this differential area. Okay, so if we want to know the total electric flux, we just have to integrate over the whole surface. Okay, this is the definition of the electric flux for any given surface. However, the interesting thing for Gauss's law is not any surface, but a closed surface. This is a surface that separates the world from inside and outside. Okay, so to clarify this, we will use as a notation this circle across the integral sign and S is just this surface, this closed surface across which we are calculating the electric flux. Okay, so once we have these concepts, these prior concepts, we can go to the formulation of Gauss's law. And this formulation goes as follows. The net electric flux outward through any closed surface equals the net charge inside divided by epsilon sub 0. This in the notation we were following, this would be that the total electric flux, which we can calculate as the integral over the closed surface S of the electric field times differential of area, this is a scalar vector multiplication, is equal to the total charge inside that surface divided by epsilon sub 0, where epsilon sub 0 is the electric constant that we've already seen several times. So let's see an application for a very simple case that we already know how to solve, but we will solve it with Gauss's law. So the first thing to apply Gauss's law, this law is always true, but it's not always useful. Okay, so it is useful only when there is a great symmetry in the problem, because we want to make simple this integral here. So to make that integral simple, we need two things to happen. On the one hand, it would be very good if the electric field is constant across the surface, or at least across the surface in parts of the surface. And the other thing is that the electric field is completely parallel or completely perpendicular to the surface. That will ease our calculations. So this Gauss's law, we have to decide which is going to be the surface S where to calculate the electric flux. So it is to us to decide this virtual non-material surface S. Okay, so the first example is the calculation of the electric field for a point charge. So we have a point charge given here. Its charge is big Q. It's a positive charge, and to decide what is going to be the surface, the best surface to apply Gauss's law, we try to see the symmetries of the problem. As we already know what the electric field is like, because we know Coulomb's law, we know that the electric field provided by a point charge is radial. So we know that a spherical shell, would be an ideal surface to apply Gauss's law, because it fulfills the two conditions we were saying that will simplify our problem. On the one hand, the electric field, if this surface, this shell is concentric with the charge, the electric field is going to be constant at each and every point of this surface. Okay, so this is going to take the electric field away from the integral. Okay, and then on the other hand, the electric field is always perpendicular to the surface at each point because it's radial. So the scalar product of the both vectors is going to be equal to the product of both modulus. So if you apply Gauss's law here, you see that Q times divided by epsilon sub 0 has to be equal to the electric field times the total surface of this shell, which is 4 pi r to the square r. Okay, so this provides the total electric field, which is going to be 1 divided by 4 pi epsilon sub 0, the total charge divided by square r, which we already knew because we already studied Coulomb's law. Okay, so let's go for another application, a bit more complicated, that we have not seen previously, using Gauss's law nor using the integrals. And this is a thin spherical shell of charge. So the first thing is to understand that this is just a shell. There is nothing inside that shell. The shell is, in this drawing, the shell is represented by this yellow shell. Okay, there is charge on it. We'll think that it's a positive charge. We'll think that the shell has a total positive. That the shell has a total charge of plus big Q, and the shell has a radius of big R, as given here. And we want to know what the electric field is out of the shell and inside the shell. So out of the shell, the first thing to do is to decide what is going to be the best surface, virtual no-material surface, where to apply Gauss's law. And if you study a bit the symmetries, you will end up realizing that there is a radial symmetry here again. So the best surface is the one given by this blue here. So this is the S surface where we're going to apply Gauss's law. And if we do apply Gauss's law, it will say that the total flux across the surface, which is the integral over the surface of E differential of area, here we have that the electric field is going to be perpendicular to every on each point of this surface, and it has always the same modulus. So it's just a matter of multiplying its modulus by the total surface, which is 4 pi square r. Okay, and on the other hand, this has to be equal to the total charge inside S, which is Q, because there's nothing else inside that than this charge, divided by epsilon sub 0. Okay, so this provides you with the electric field that is going to be equal to 1 divided by 4 pi epsilon sub 0 BQ divided by small r, square small r, which is just exactly the same electric field as if all the charge was concentrated in the center of the spherical shell as a point charge. Okay. However, inside the spherical shell, things are different, and this is because if you apply Gauss's law to a surface inside the shell, like the one I'm applying, I'm trying to plot here in red, and you try to apply Gauss's law, then you end up showing that there is really no charge inside that surface. Okay, inside this S, there is no total charge, there's no net charge, so the electric field has to be equal to 0, and this is what is represented here. So inside the shell, the electric field is 0, and then the electric field is equal to, at this point, it's equal to Q divided by 4 pi epsilon sub 0 big R square big R, because this is this dimension, and then it just decreases with square R. Another similar example is using an uniformly charged solid sphere. So this is a sphere, this is different from before, because this sphere is completely solid. So it's not a shell, it's completely solid. So we're going to denote this sphere. It's going to have a radius big R, and the total charge is going to be big Q. Okay, so very similar as to what we had before. If we are seeking to find the electric field outside of this solid sphere, we would first have to decide which is the best surface where to apply Gauss's law. And given the symmetry of the problem, this is going to be again a spherical surface with the same center as the solid sphere. Okay, and this is denoted by this blue. So this is S, where we apply Gauss's law, and it's the best because there the modulus of the electric field is equal at each point of the surface, and because this electric field is perpendicular to the surface at every point, so we end up having just the same expression as the two former examples, and that's why for R bigger than big R, we have the same type of electric field as if we had a point charge with all the charge concentrated in the center of the sphere, of the solid sphere. However, inside things are different. Okay, so now we want to understand what is going to be the electric field inside. So this here now represents the solid sphere, and inside we have to define what is going to be the best surface where to apply Gauss's law. And again, the symmetry is radial, so again the best surface is going to be a spherical shell, which is provided by this inner shell here. This is S. Okay, So if we apply Gauss's law there, we will have that the electric field, if we call small q to the total electric field inside this sphere here, we will find that the electric field for a radius r, which is smaller than big R, is given by this expression here, okay? However, small q is not equal to big Q, because small q is the charge that is just inside this surface here, okay? So to relate both, we can use the density, the volume charge density, rho, and we can find out what the relationship between both are. And if you see here, the relationship is that Q is dependent on small r. So if you put everything together and you express it as a function of big Q, you find out that the electric field inside the solid sphere is varying in a way proportional to r. So this graphically is given here. So from the center where the electric field is 0 because of symmetry, up to its radius, the electric field is growing in a way proportional to r. Okay, so this is the curve here, which is just a straight line. And outside of this solid sphere, the electric field just is the same as if all the charge was concentrated in the center, which is given by this expression here. The last example I wanted to tackle with Gauss's law is an infinite plane. So imagine we have this infinite plane. We can think of an infinite plane. I'm looking at the infinite plane from one side. So my eyes are here, and I see it like this. I think it's positively charged. So to find what is the best S to the best surface where to apply Gauss's law, I think of a point here, and I think what the symmetries of the problem are. So first I want to know what is the direction of the electric field here. And we can discuss, and you will find that this electric field has to have this direction, because if we think of a point just below it, it will give you some electric field that is going to have this direction. If we think of some point here, it will have this direction, but we can always find a symmetric point that will give you this direction. So these two will cancel out in the x direction, and you will only have electric field in the direction perpendicular to the plane. Okay. Then another thing is thinking if the electric field in this other point is equal or different from the electric field at this point here. And if you just think of moving to the right or to the left the plane, you will see that nothing happens, because this plane, nothing changes, sorry, because this plane is infinite. So you end up showing that the electric field at this point has to have the same direction and the same magnitude as the electric field at this other point here. So the best surface to apply the Gauss's law is the one provided here in blue, which is a cylinder with an area A on the lids. Okay, why? Because in this area of the lid, the electric field is going to be always has the same magnitude and direction, which is perpendicular to this surface, to the lid in each point. Also in the lid that you have below, but which we don't see because there's a plane. And then in the sides here of this surface, virtual and non-material surface, the electric field is parallel to the surface, so the total flux there is 0. So the total flux given across this electric field is going to be twice the electric field times the area. Why twice? Because we have two lids, the one up above and the one below. Okay, so this gives you this two, and this has to be equal to the total charge inside that surface. The total charge inside that surface is given by the portion of the plane captured by the cylinder, which is just sigma times the area divided by epsilon sub 0. Careful here, because there is an epsilon sub 0. It needs an epsilon sub 0. So we just take away both a's, and we end up showing that the electric field provided by an infinite plane of uniform charge is given by the charge, the surface charge density divided by 2 epsilon sub 0. I hope you found this video useful, and see you in the next one.